Earlier we had looked at the two-level atom which is being impinged by a strong radiation field. The field was near resonant, and one of the most important lessons that we learned from there was that in steady state, as the field gets stronger, the population difference between the ground state and the excited state nearly disappears. That is, even if you create population inversion, very quickly the population inversion is lost if the coupling between the atom and the field is only radiative within the two states. So that is a very important lesson. Now we want to try and obtain the possibility of lasing. That would imply a possibility of achieving population inversion in the steady state. This requires us to at least go beyond the two-level model, which simply had the atom, and we had approximated the atom to only the two levels involved in the transition and the corresponding field. So what we will do now is to take a step towards this generalization. We look at a simple model, and this would involve three levels within the atom. And by the way, this is not that abstract a proposition, because the first ruby lasers that were made were actually relied on a more complex, but yet this three-level model captures the essence of how the ruby laser is driven. Let's get to the simplified model. There are going to be few takeaways from this lecture. One is that we are actually constructing an extremely simplified version of the atom light interaction. Yet, the lessons one learns are actually quite close to reality. So, that is the power of making the right approximations and capturing within your simple model the essential physics of the problem. So, this is one such example of that. Let's consider the three-level atom. Again, what I mean is I am neglecting all the other states within the atom and restricting myself only to three levels. So this is my ground state. Level 2 is my excited state, and level 3 is another excited state. So I will try and stick to the uniform notation. That is, my 2-1 transition is the lasing transition. What I mean by that is H nu 21 corresponds to the energy associated with the lasing transition. The frequency which is nearly resonant to this transition, this is the radiation associated with that transition. So what one is saying is that along the 2-1 transition, the radiation which is generated is what is captured by the feedback system, that is our mirrors that form the cavity within which the active medium is, right? So, and that radiation is what is being built up as the lasing radiation, and hence I'm calling this to be the lasing transition. Then I have a decay rate from level 2 to level 1, and I'm calling that decay rate as gamma 21. Contribution to gamma 21 might come from the spontaneous emission rate, or it could even come from losses which are there from the excited state out of the system, right? So that is another contribution that could be there, but that essentially captures my gamma 21. What I have is I am somehow pumping the population from ground state to the excited state denoted by 3, and this is my, I'm doing a radiative pumping at the rate of P, and there is a decay which is non-radiative, which is between the levels 3 and 2. I'm calling this as gamma 32, and let me qualify all of these. This is a fast decay. What that means, moment there is a population in level 3, it quickly decays into the level 2. Then the gamma 21, or rather this transition is the lasing transition. this is the pumping that is required to create the population inversion between the states 2 and 1, right? And the other important thing is that my level 2 is long lived, or it is meta stable. All right. So this is essentially the model, and my what I'm going to do is to write down the rate equations that govern this model. Is that okay? So let me define a few variables. For example, Ni is going to be the number density of atoms in state I. So N1 is in state 1, N2 is in state 2, and N3 is in state. Just a note. So for example, if I am looking at uh, P, which is the pumping rate, so P times N1, for example, this will give me the number density of atoms which have been taken from the level 1, right? They have been pumped out of the level 1. So number density of atoms, and this is a rate. So it is number density of atoms per second taken from level 1. All right, so let us now look at various mechanisms. So what I'll do first is to talk about the pumping route, right? So the pumping route is such that there is a change in the rate of the population in the level 1. So dn1 over dt gives me the rate of change of population due to pumping. I'm now focusing only on pumping. I'll add the decays later. And this is simply minus p times n1. This pumping leads to a change in the population of level 3, and that precisely is the positive of that number. So p times n1 is the rate at which the population in level 3 is being changed due to pumping, right? So we are pumping the atoms from the ground state, which is level 1, to the higher excited state, which is level 3. Now, my claim is the following. So I'm making a few approximations, and that the decay from level 3 to 2 is extremely fast. That would mean hardly any population would stay in the level 3. Most of the population will be quickly, the moment it reaches 3, would be dumped back into the metastable state 2, which is the excited state of the lasing transition, right? The metastable state 2. So the claim I'm making is that dn2 over dt, right, due to pumping, of course, this is almost equal to the rate at which the level 3 is being pumped. Actually, it's exactly equal in our model here. That whatever is put in level 3 quickly goes into level 2, and we know what that is, right? This is precisely equal to minus times uh, minus dn1 over dt due to pumping, right? So this is an assumption that I am making, and this assumption has got to do with the fact that gamma 3.2 is much larger, that the rate is much larger than either gamma 2.1 or the pumping rate or any other time scale that is involved in the problem, right? So this is a major assumption that I have made. Now let's look at the decay processes. So let me look at the decay in my model. So we see that so dn2 over dt due to decay, this is the decay governing the level 2 is simply arising out of this gamma 2.1 rate, so which is simply minus gamma 2.1 times n2. I am essentially what I have done is I have got rid of the level 3, stating that whatever I put in level 3 actually lands up in level 2. So I'm not looking at it as a decay rate, but that contribution I'm looking at as a pumping. Uh, so that is one statement. And of course, dN1 over dt is going to be the recipient of that. The decay rate actually leads to increase in the population, in the ground state population. You'll be able to write down the rate equations governing these processes. Essentially what we have, that the level 3 barely participates in it because it's simply a conduit through which the population, the pumping, takes the population from the ground state to the metastable state 2, right? So let me write down uh, the rate equations for the whole system, that is including the radiation. So you have dN1 over dt. The contributions to the change in population is simply coming one from the pumping, so it's minus p times n1. This takes the population through the level 3 to the level 2. Then there is the increase in the ground state population due to spontaneous emission and decay from the level 2. And then there is, of course, the uh, coherent interaction between the field, which is sigma times phi nu, which is the photon flux of the lasing transition. Now, these are the lasing photons, and times n2 minus n1. This captures for us the increase in the ground state population due to stimulated emission, and then increase in the decrease in the ground state population due to absorption, right? So these are the two contributions that we have written down. Similarly, one can write down the rate equations that govern the excited state population or the level 2 population, which I called as metastable, as they are these are long lived in comparison to the uh, decay that we talked about earlier. So dN2 over dt, the dN2 over dt due to pumping is precisely what it has got from the level 1, that rate. So that is simply plus p times 1. And then you have the spontaneous emission decay rates and times the coherent interaction with the field, where again the first term here tells me that there is decrease in the excited state population because of stimulated emission, and there is an increase in the excited state population because of absorption, right? So this takes care of, so this is our equation number sort of 1 and 2, which I have written down for this three level system. And my claim is that level 3 for all practical purposes remains 0. That is, the conservation of the population effectively is simply n1 plus n2. This is my total number of atoms. There is hardly any atom that stays in the level 3. So that would mean that my d by dt of n1 plus n2, you can check that indeed that is true, is actually 0, which implies that n1 plus n2 is a constant. And we know what that constant is. That is simply the total number of active atoms. All right, so just a point to emphasize, uh, two issues. One is that gamma 32 is a fast decay. How does this decay happen in typical active media? This decay happens due to non-radiative processes. For example, chromium atom in the ruby laser could lose this by shedding away this energy to the crystal. What happens is essentially the crystal temperature rises. So it's a loss through a pathway which is governed by phonons or the crystal vibrations. And the level 2 is chosen such a way that it is metastable, in the sense that when the population arrives in level 2, we want that population in level 2 to remain long lived in the sense that hopefully it will be stimulated emission that will dominate the population accumulation in the excited state, and not spontaneous emission. If it's a short-lived state, then most of the population in level 2 will be lost through spontaneous emission. And we know that spontaneous emission is a source of noise in our lasing system. So that is a loss mechanism. So what we would like to do is to retain as much as population inversion that we create in the level 2, hence that is called a metastable state. Right. So now let us look at these two equations and see whether we can learn something from these two in the steady state. After all, we are looking at a CW operation, and let us see whether we can look at it in steady state. So please note the forms of this equation. So let me do first let me do a approximate study, right? And then I will do a more complete version of it. So the approximate study is the following. So let me consider now the the business of threshold, right? So let's look at threshold. You know what threshold means. So threshold is simply a condition which captures the loss in the system. If I am at threshold, you see that the number of lasing photons, phi nu, okay, is quite small. Remember, at precisely at threshold, we have just managed to equate the gain to the loss, right? So gain equal to gain threshold is a condition where we have just optimally just overcome the losses. So the lasing number of photons is still quite small. So what I will do is at threshold, so phi nu, this is at threshold, mind you, and so I'm going to neglect this interaction with light. Let us see what we get, right? So I'm looking at now steady state. Let's be very clear, this is steady state at threshold. I can set my dn1 over dt to 0, and similarly I can set my dn2 over dt to 0. After all, we are looking at steady state. So if you simply look at these two equations and we ignore this second half of the equation that is dependent on the field strength or photon flux, so then we are left with two simple set of relationships that give us the following. So I will use basically the third equation as well. This is equation number 3, which is simply the conservation that n1 plus n2 is total n. So I can write down n1. I'm denoting the steady state by a bar. So n1 bar tells me the steady state population in level 1. So once I implement this threshold condition, what I get is that my n1 bar is simply gamma 21 divided by p times n2 bar, right? And also I have the equation number 3, which is that my n1 bar plus n2 bar is indeed the total number. So what I get, let me call this as n total just to make sure that we are there. So I can essentially obtain from these two equations what is my steady state. So n1 bar is simply gamma 21 divided by p plus gamma 21 times n total, and n2 bar, this is a steady state value, is p by p plus gamma 21 times n total. So now if you look at this, now one can ask what is the steady state population inversion, and that quantity is simply n2 bar minus n1 bar. Remember, this is the population inversion, and this quantity is simply p minus gamma 21 divided by p plus gamma 21 times the n total. Now you see, it is very clear that for inversion to happen at steady state, that is, we want this n2 bar minus n1 bar to be positive, and that implies that for inversion, what I require is my p should be larger than gamma 21. So this is essentially what is required for us to get non-trivial gain or population inversion on the lasing transition. So clearly P minimum required is actually gamma 21, right? This is a very interesting result. It is telling you that the spontaneous emission rates or decays of the level 2 into non-lasing parts of the system, you need to offset at least that much loss for you to start getting non-trivial population inversion. This P minimum is what I would call it as my threshold pumping rate. Now let us kind of estimate what does this give you. Let's look at the power that you need to deliver per unit volume for to these active atoms. So let us do that quick calculation. What I'm asking is what is the power I need to deliver per unit volume of the active medium to achieve this kind of pumping. So that I am writing it as, remember the radiation that does the pumping, right? It is the radiation that matches the transition H nu 31, right? It is between the states 3 and 1. So let me quickly draw here the level diagram. So this is my 1, this is my level 2. Remember that the lasing transition is there, but my pumping rate is taking me to level 3. So this is the amount of energy that I need to uh, put in on the collection of atoms in the level 1, right? Of course, I'm talking about steady state, so it's N1 bar, and the rate at which I'm putting uh, the the pumping, the power for pumping is simply just this. So this product is going to give me essentially the amount of power I need to deliver per unit active atoms, right? So this I can rewrite quickly from what I have seen as simply H nu 31 times P, and now replacing the expression for N1 bar, which is written here. So it is simply P times gamma 21 divided by gamma 21 plus P, right? And this multiplied by the total number of atoms. So essentially what I have is the following, that the power per unit volume, and I'm talking about the minimum power required now. At minimum power, what happens? P is equal to gamma 21. So I can as well write this as half times H nu 31 gamma 21. I have eliminated essentially P. P is just the P minimum times N total. So before I go further, I just want to describe for you very briefly the Ruby laser, so that you can connect what we have done until now to a real example. So the Ruby laser consists of chromium atoms which are doped in a matrix of Al2O3. The the aluminum 3 plus ions are replaced by uh, chromium, and this is the chromium is simply 0.05% by weight, right? That's a kind of you know uh, doping levels of chromium that you get. And for pumping, what one uses is radiative pumping, where one puts in either xenon or mercury flash lamps for pumping. So these are lamps which have got roughly the transition of the greenish variety. So it's about 550 nanometers. That's a kind of light that you require, lambda pump. And so let me quickly draw the level diagram. So what you have is the lasing transition, which is level 1, level 2. This is my lasing transition, and there is a family of states here, which are huge number of them. And these states are, what I'm saying, are centered around this 550 nanometer transition, and that is where the pump uh, P is being applied, right? And there is a non-radiative decay rate, which is of the order of 10 to the power of 7 per second inverse, is the kind of decay rate which is gamma 32. So what one has done is to claim that this is rather than a band of states, one is replacing that in a simplified model as simply level 3, but that is actually a set of states there, and they all decay into the excited state 2, and the gamma 2 1 associated with the ruby is of the order of about 500 second inverse. So that is half times 10 to the power of 3 second inverse. So that's a kind of typical lifetimes of these states. So we are looking at a millisecond kind of a lifetime in comparison to these fast decays, which is a fraction of a microsecond, right? The typical number densities of chromium atoms uh, is of the order of 1.6 times 10 to the power of 19 per centimeter cube. So that is the number density of chromium atoms. Um, the the lambda here corresponds to energy. So we are just looking at in centimeters and so on. So let's convert this into ergs. This 3.6 into 10 to the power of minus 12 ergs, right? This is simply hc by lambda rather than SI. We use CGS units there. Now let's estimate what we got, which is the power per unit volume and the minimum I need to provide for a ruby rod. Okay, so let me just again emphasize the typical ruby is actually in form of a rod, right? It's kind of a rod, and the typical radius is of the order of, let's say, 2 millimeters, and the length of the ruby rod could be about 5 centimeters. That's a kind of active medium, that's a kind of volume and the size of the active medium that we are talking about. Okay, so the power which I need to deliver, right, minimum power to just essentially get to threshold, right, is simply this quantity. It's half times gamma 1, which is half times 10 to the power of 3 second inverse, right? This multiplied by the number of atoms doped, which is 1.6 into 10 to the power of 19 per centimeter cube, now times the corresponding energy of the pumping photon, which is simply 3.6 into 10 to the power minus 12 ergs. So if you put this all together, so the power per unit, you'll see that this will come out to be about 10 to the power of 3 watts per centimeter cube. And now if you are looking at a ruby rod, so the power which I need to deliver to the ruby rod of that size, right, is simply this 1 kilowatt per centimeter cube times pi times zero point 0.2 pi r square, right, 2 millimeters times the 5 centimeters. And you see that this comes out to be about 600 watts. So, roughly this is the kind of, power levels one is talking about in a situation like this. But I want you to realize that this is the power that needs to be delivered to the active atoms that participate in the pumping process, right? So when we use this flash lamps like xenon or mercury flash lamps, you see that these are lamps that rely on excitation of xenon or mercury atoms when they are bombarded with electrons, right, inside a discharge. So these flash lamps invariably lead to emission which is rather broadband. There is a lot of energy lost in heat itself, and there is a narrow spectrum which is around the 550 nanometers which needs to couple to my active atoms, and not all of that actually couples. So roughly you have efficiency, which is extremely small, of the electrical power that you use to drive the pumping and what is actually absorbed by the atoms in a particular transition, and the kind of efficiencies one is talking about is much less than 1%, right? So one needs to actually drive it much harder to generate this pumping to be converted into useful lasing radiation. So these days, of course, there have been improvements in these processes. So nowadays, you would find lots of these solid state lasers are pumped by diode lasers, which are themselves extremely efficient. So you typically have a diode pumped Nd:YAG laser or things of that kind, where you are now choosing the pumping radiation to be extremely narrow band that precisely couples to your this 3-1 transition, for example, in our case here. You do not waste the energy put into the pump in various other detrimental channels, and it is utilized only for creating the inversion. Hope is that the intrinsic quantum efficiencies should dominate the laser. One has to look for mechanisms or look for physical processes that will help you increase the efficiency of pumping. The other important detail which I want to give you is that this transition, the lasing transition of the ruby laser, is actually homogeneously broadened. Delta nu naught, which is the broadening, is roughly of the order of 170 gigahertz, right? This is a fact, and this we are talking about at the ruby lasing wavelength, right? Ruby lasing transition is 694.3 nanometers. The A21, or rather the spontaneous emission lifetime, is just about 230 second inverse. It's really a long-lived in terms of spontaneous emission. So I can estimate, the sigma max, right? That is, I come at resonance and ask what is the value of that. That will simply come out to be, so I have lambda square divided by 8 pi. You will recall this formula that we had discussed. We have A21 divided by n square. Remember, we are now looking at a solid state laser. So the refractive index of the ruby rod, which is coming from the Al2O3 matrix, background matrix, that is about 1.76. And because it is Lorentzian broadened line shape, you see that the maximum value will go like pi times delta nu naught. So if I plug in all these values which are given to you, you will see that this comes out to the order of about 10 power minus 20. So 2.7 10 to the power of minus 20 centimeters square. So please undertake these calculations for yourself, and to arrive at the gain threshold, remember what I require is the reflectivities of the mirror. So again, let me give that information. So let's say the one of the mirrors has got a reflectivity 1. The output mirror has got a finite reflectivity about 0.96. And then I'm saying that let there be, I'm giving you typical numbers of this. Let there be 3% loss per round trip. This is the distributed loss. So if you put these numbers together, you see that I can write down my G threshold as 1 by 2L. Remember that I'm looking at the rod of length 5 centimeters. So 2 times 5 centimeters. That's my gain medium's length. And now you're looking at log of 0.96 plus we are looking at a 3% round trip loss. So 3% would imply it is 0.03, that is 3 divided by 100 divided by, that's per unit length, which 2 times 5 centimeters. So what we get here is my G threshold comes out to be 7.1 into 10 to the power minus 3 centimeter inverse. So once you have the gain threshold, from there one can get n2 bar minus n1 bar threshold, right? Let me call this as delta n threshold, and this is simply the G threshold divided by the sigma max, right? So you see that this comes out to be 7.1 times 10 to the power minus 3 divided by 2.7 into 10 to the power minus 20 centimeters square. So my delta N threshold comes out to be 2.6 times 10 to the power of 17 per centimeter cube, right? This is a number to be compared with the total number of atoms which are there, right? Remember the total number of atoms were about 10 to the power of 19, so which seems reasonable. So before I go ahead, I want to present to you a generalization. So rather than looking at a three-level scheme that we looked at uh, just now, we are going to look at a four-level uh, scheme. And let us see if there are any advantages. So the idea is the following. Remember in the three-level scheme, what we had was the population was being taken from the ground state itself to the excited state, and then there was a non-radiative transition that got it to the lasing transition. In here, what we want to do is remember that our purpose is to obtain inversion, that is largest value of N2 minus N1. So in the three-level scheme, we were increasing N2 and hoping that N2 minus N1 will become large. In the four-level scheme, what one does is not only increase N2, but also decrease N1, right? So take away the population from the ground state, if possible, and create this inversion, which could be beneficial. What we're talking again is not something very esoteric. It is indeed used in the ND-YAG laser, which is another workhorse of a high power laser in the lasing industry. And ND-YAG laser does have this kind of equivalent level scheme that one can talk about. Let me show you the level diagram. So I have ground state is, let me call this 0 now. My lasing transition, I want to stick to the ground state of the lasing transition is 1, and the excited state is 2, and the state is 3, right? So this is my four level system. And what I'm doing is I'm putting the pumping all the way from the level 0 to the level 3, and this is my pump rate. There is a fast decay rate gamma 32 between the excited state 3 to the lasing transition excited state 2. My lasing transition indeed is 2 1. We'll stick to that. There will be a decay here which is gamma 2 1, and there is another decay within the lower states, and this is given as gamma 1 0. So I'm looking at a situation where gamma 32 and gamma 1 0 are extremely fast, right? So they are the dominant rates. So again, I need to now write down the equations which are governing this level scheme. We'll again make the similar approximation stating that my level 3 remains nearly 0 because all the population that goes into level 3 actually quickly decays to level 2, right? And the level 2 is metastable, right? The atoms in thermal equilibrium would largely occupy the state N0. So, and in thermal equilibrium, imagine that my N0 is essentially close to the total. For most practical purposes, that's where the population would be. But of course, now the lasing is not uh, directly connected there, but again, you have a decay which is from 1 to 0. Now, note that all these decays, gamma 32 and gamma 10, are all non-radiative in nature and they are extremely fast. Their rates dominant in the present consideration. All right, so I will write down quickly the rate equations. I'm sure you'll be able to do that yourself. So I have dn0. Remember that even though my level 0 does not participate in the lasing, I cannot ignore the population in the ground state, because clearly ground state is always mostly occupied. So I will have to include whatever be the considerations that I might have. I will have to include the ground state population uh, into my uh, into my rate equations which govern this lasing. So dn0 over dt. So the ground state population is lost due to pumping, and it increases due to the decay from the level 1. And then I'll write down the two equations governing the lasing transitions. So of course there is a gamma 21 N2 that increases the ground state population through decay from along the lasing transition route, and there is gamma 10 which decreases the ground state population to the final state 0, and there is of course the sigma times phi, which talks about the lasing photon flux times n2 minus n1. Now dn2 over dt, which is the excited state of the lasing transition above, is loses through spontaneous emission. Indeed, it gains through the pump, which is just P times N naught. Remember, I'm saying that my level 3 is just like we had done in the previous model. The level 3 is eliminated, and we're looking at direct, almost nearly direct pumping of this from the ground state. And then you have sigma times phi nu times N2 minus N1. These, of course, take care of the stimulated and absorption processes which are coherent. Most important approximation that I have made here is in terms of the pumping rates, stating the following: that my dn2 over dt, all this due to pumping, equals the state dn3 over dt due to pumping, which is equal to minus of dn naught over dt, and this rate is simply p times n naught, right? So whatever is starting at level 0 due to pumping is quickly dumped into the level 2 due to pumping. So that's the main assumption that we have made. Now again, I'm going to look at the steady state, and let me write down the steady state results. You can do this yourself and check it out. So what we get is the following, and I'm looking at threshold. So let us be very careful. I still want to ignore the I still want to include the photon flux, which is negligible. So phi nu is being ignored, right? So if I just look at the steady state population, I would get the following at threshold. So my n naught gamma 10 times gamma 21 divided by this multiplied by the n total. Similarly, n1 bar is gamma 21 times p times n total divided by the same denominator, and n2 bar is the following. Now, clearly, given this, uh, I have again, let me go up, and I have again used the fact that n0 plus n1 plus n2 is my n total. Remember that the level 3 remains more or less empty in this whole process. So I can write down my population inversion, which is n2 bar minus n1 bar in the steady state, to be the following. It is basically p times gamma 10 minus gamma 21 times the n total divided by the denominator, which, as I said, is simply the following. So now you can clearly see that if we choose, so this is important, if we choose that my gamma 10 rate is larger than gamma 21, let us quickly identify that. What one is saying is that this decay mechanism in the ground state, if this is larger than this decay mechanism, right? In that case, there is always inversion if P is non-zero. So, right, for gamma 10 is larger than gamma 21, you see that this quantity is going to remain positive for P non-zero. Any pumping is sufficient to create this population inversion. If we choose gamma 10 to be much larger than either gamma 21 or even the pumping rate, right? This is simply depends on the choice of transition and the mechanisms of decay that one can incorporate, right? It is got to do with the very intrinsic properties of the active atom, the level scheme, and the surrounding of the atom that basically dictates this non-radiative decay in the ground states. If so, that is the most dominant mechanism. If this is true, then you see that I can write down my N2 bar minus N1 bar to be simply, so gamma 10 is dominant. So you see I can ignore my gamma 21 there. So I see what I get is simply P times N total, the following, gamma 21, right? And now one can ask the same question that we asked earlier. Power per unit volume I need to deliver for such a four level scheme, right? Let me call that 4. So, and I know the following. So I need to provide energy of h nu, but now the energy needs to be provided for the pumping between the levels 0 and 3. H nu 30 is the kind of energy required there, and this I need to deliver to the population in the level 0, and I need to deliver uh, at the pump rate P, right? This is the pump rate for the 4 level scheme. I know from here, I know the following, that my delta N, let me call that threshold. Now let me look at the minimum power required. So delta N threshold is simply P threshold plus gamma 21, which is equal to P threshold times N total, right? I can quickly rewrite this as that delta N threshold times gamma 21 equals to P threshold times N total minus delta N threshold, correct? I've simply rearranged this relationship, and you know clearly that my N total is always much larger than delta N threshold, right? We'll even calculate this if for the example, but that is clearly true. So you see that I can replace my power per unit volume as h nu 30 times P threshold. Now I'm looking at the minimum power required times N naught is more or less the total N, right? Because in comparison to the inversion and all that, the ground state population is essentially the most occupied. Uh, so what one is saying here is that my N1 and N2 are much smaller than N naught, and hence uh, N naught is equal to N total. Right. So I know that this product from here is simply the following. It is h nu 30, right, times delta n threshold times gamma 21. right? This is the kind of relationship we get. Now remember that the power per unit volume that we got for the three level system, it again involved energy associated with the pump, but it involved the total number of atoms which are present, not the delta N threshold. And imagine that gamma 21 was commensurate, then both the cases it is equivalent. So you see clearly the power per unit volume required is much smaller because this quantity is proportional to now delta N threshold in comparison to the total number of atoms which was there in the previous scenario. Right. So let me just again quickly give you the numbers for the ND YAG laser. You will understand the level scheme as well as the simplicity that arises out of this. So my whole interest is to compare it with the ruby laser quantities that I got. So what is ND YAG is you have a neodymium atoms, right? These are doped in yttrium aluminum garnet. This is a crystal, right? It is Y3 Al5 aluminum 5012, right? This is a transparent crystal, and the gamma 21 associated with this NdYAG, the transition is actually 1800 second inverse. The lambda is 10.6 micrometer. This is the lasing transition associated with the NdYAG. At 300 Kelvin, right, the cross section is roughly of a similar order. Remember, it was 10 power minus 20. This is about 10 power minus 19 centimeters square. And imagine that we had the same gain threshold as our previous scenario, right? Which was about 7.1 into 10 power of minus 3 centimeter inverse, right? I'm looking at a similar commensurate size of the rod, the a similar cavity and so on to give you the gain threshold. This implies that my delta N threshold is not very different because my sigma as well as my G threshold was comparable, and this comes out to be, from these two quantities, 8 into 10 to the power of 15 atoms per centimeter cube. So that is the number of basically the number density of atoms involved in the threshold, right? Uh, which is probably again sort of comparable that what we had. So the NdYAG level scheme, again, it can think of it as a four-level system. What you have again is a family of states here. These go all the way from 2.6 into 10 to the power minus 12 ergs, all the way to 6 into 10 to the power of 12 ergs. Let me look at an average. That's my pump. And then there is a fast decay. There is a fast decay here. And that's a lasing transition, right? So that's my NdYAG this thing. So I'm looking at now power per unit volume for such a laser, and that is simply, so this average is roughly about of 3.8 12 ergs times 8 into 10 to the power of 15 atoms. Remember, it is proportional to the inversion and not to the total number of atoms doped, times the excited state lifetime, which is 1800 second inverse. So here what you get, you will see clearly it is just 5 watts per centimeter cube. Remember, in comparison to 1 kilowatt per centimeter cube, this is the kind of number that one is looking at. So literally, that is the kind of advantage you get. So what one is doing is stripping off the population from the ground state to create the inversion. All right, so next I'm going to look at, we'll go beyond the threshold and see what happens in presence of a strong field.